Yeah, good morning, students. Am I audible? You all are from section B, right? Okay. So, in the last class, we have solved one numerical related to our profile. Okay. So, some of you have some doubts. So, we are going to solve another one. Okay. It's just a similar type what we have solved in the last class, but with a different problem. Okay. So, you kindly write down this second problem. Okay. So, here a rectangular channel is given of 5 meter wide, carries water at a depth 1.5 meter. Okay, so depth of flow is 1.5 meter. Bed slope is also given, it's 10 to the power minus 4, and Manning's roughness n roughness coefficient n is also given, that is 0.016. And what it says, the ends in a drop canal or canal drop. I think that canal drop or canal fall, I think you have studied in irrigation. Okay, so that canal drop and canal fall is not related to our syllabus. Okay, you can study this thing related to your irrigation. Okay, so just you have a channel, and in the end of the channel we have a canal drop. Okay, so now we need to find out the profile. Okay. Okay, so here previously the depth of flow is 1.5 meter, and after this canal drop our depth of water reduces to 1.4 meter. Okay, so now what we have to do, we need to find out the profile. So first you write down the question, and in previous case it was a trapezoidal channel, here it's given rectangular channel. Okay, here it's given a rectangular channel. Over the So similarly, we need to first find out the velocity. Okay? As Manning's n is given, so we are going to use Manning's equation to find out the velocity. Okay, so the depth of flow is given 1.5 meter, width of the channel is 5 meter wide. Okay, so you can find out the area and weighted perimeter. Okay, of this rectangular channel. Okay, so area and weighted perimeter you can directly find out. So area will be into y, so 1.5 into 5, and your weighted perimeter will be 1.5 1.5 multiplied by 2 plus 5. Okay, so this will be your weighted perimeter. So here then you substitute here in this equation, and value is already given, that is 0.016. Bed slope is also given, it's 10 to the power minus 4, 10 to the power minus 4. And area and weighted perimeter you can easily calculate. Okay, and you find out the velocity. Over, you're all are getting the same value, that is 0.60 meter per second. After calculating velocity, you need to find out the discharge. Okay, discharge is nothing but area into velocity. Okay, area into velocity. And actually our intention is to find out the small q. If you remember, small q is nothing but discharge per unit width of the channel. Okay, so here in place of discharge you can write area into velocity. In place of area it is b into y. Okay, multiplied by velocity divided by capital B. So this B will cancel out. What will be left out? Velocity into depth of flow. That's why they have written here V into Y. Okay. So don't confuse. This is nothing but your discharge per unit width of the channel. Okay. So for rectangular channel, you can directly write V into Y, or you can do like this also. It's up to you. Okay. First you find out the discharge, and the width of the channel is already given. So you divide the discharge by width of the channel. You will get the small q value. Okay. So first, what we did, we need to find out the velocity using Manning's equation, because the Manning's n is already given in the question. Okay. If in place of Manning's n, Cauchy's constant is given, then we use Cauchy's equation to find out the velocity. Okay. Then you find out the velocity, and after velocity you got, then you find out the discharge. Ultimately, we need to calculate small q, that is your discharge per unit width. How much you got? Small q value, it's 0.90. Okay. So after that, we are going to use our critical depth equation of rectangular channel. Okay. If you remember, yc cube is equal to q square g, q square divided by g. Okay. Or you can write, or yc is equal to q square divided by g to the power 1 by 3. Okay. It's to the power 1 by 3. So you use this equation and find out the yc value. What you got YC value? Yes, it's correct. Okay, 0.435. Okay, so after that, you need to find out the FR value. That is your proud number. Okay, this will be 1. Okay, so we need to find out the FR value. FR is nothing but your proud number. That is your Vy root over GD. Okay, D is hydraulic depth. That is nothing but area by top width. Okay, as we know, area of a rectangular channel is B into Y, and top width of a rectangular channel, you can say it's a B. Okay, rectangular channel, your bottom width and top width will be same for a rectangular channel. Okay, so in place of top width, you can write B, and this will be cancelled out, and it will be Y. So that is why for rectangular channel, when we calculate for Froude number, we can write directly root over GY. Okay, but this equation you cannot use for other cross section or other channel shape, that is your like a trapezoidal, triangular, or any other shape. Okay, this is only valid for your rectangular channel. Okay, so you can use this expression and find out the Froude number. Velocity, I think we have already calculated. G is nothing but 9.81 and depth of flow is 1.5 meter. Over how much you got? Yes, correct. Okay, so your whatever the value you are going to get, we are going to compare that value with 1. Okay, if it is less than 1 or it's greater than 1 or it's equal to 1. Okay, so whatever the value you got, suppose here we got 0.156, which is less than 1, which is less than 1. So now we go back to our specific energy curve. Okay, that day also we discussed this curve. I'm going to discuss today again. Okay, so in x-axis we will be having our specific energy. Okay, and in y-axis we will be having our depth of flow. Okay, so now this line is called specific energy is equal to depth of flow. Okay, and it's at an angle of 45 degree. Okay, it's just a straight line, imaginary line, when your specific energy and depth of flow will be same. Okay, so for a particular discharge, if you draw a specific energy curve, it will follow this pattern. Okay, it will follow this pattern. Or if you see in this way, it's increasing, increasing. Sorry, it's reducing because this is will be the higher value. Okay, for specific energy, if you see, this will be your higher value. This is your higher value. Okay, if you see, it's reducing, that specific energy with respect to depth is reducing. We are increasing depth and your specific energy is reducing, and then it reaches to a minimum value. After this, when you again increase the depth of flow, our specific energy again increases. Okay, so here if you see, for a smaller depth, if you see, when you increasing the depth, initially your specific energy is reduces. Okay, it reduces and it reaches to a minimum value. After that, if you increase further depth of flow, your specific energy again increases. Okay, in this direction again increases. This point, this point is called our minimum specific energy, and this specific energy, that corresponding depth is called your critical depth, or you can say YC. Okay, understood? So in our case, our minimum specific energy is at depth of 0.435 meter, because YC value we have already calculated. Okay, for this depth, whatever the energy you are going to calculate, that will be our minimum specific energy in that particular case. Okay, okay. So now if you draw a straight line by crossing this minimum specific energy, it divide the whole specific energy curve into two parts. Okay, one is supercritical, one is subcritical, SUB. Okay, so in supercritical, your depth of flow is always less than YC. By this diagram, you can easily identify whatever the depth of flow is there in supercritical is always less than YC, because the supercritical portion is below the critical or minimum specific energy. Whatever the depth you are going to find in supercritical is always less than YC value. Okay, and vice versa. For subcritical, it is always more than YC value. Okay, and for this minimum specific energy, or you can say critical depth of flow, your Froude number is equal to 1. Your Froude number is equal to 1 for this particular YC value. Okay, for any value in subcritical, your Froude number is less than 1. Okay, or any value for supercritical, your Froude number is greater than 1. Okay, so by this Froude number, you can identify that your flow is in subcritical, or is in critical, or it is in supercritical. You can identify. Once you find out the Froude number, you can easily identify that your flow is in subcritical stage, or supercritical stage, or in a critical stage. Okay, so here in our case, if you see, our value for Froude number is 0.156, which is less than 1. Okay, so that means when our Froude number is less than 1, that means our flow is in subcritical. Okay, here. Okay, okay, so our flow is in subcritical, and in subcritical we all know our depth of flow is always greater than YC value. Okay, from this diagram you can easily identify if a flow is in subcritical, then the depth of flow is greater than YC value. Okay, that means your YN, or you can say whatever the value, is greater than your YC. Okay, understood? Okay, so For identifying the profile, we first identify the slope, that the channel slope is mild or steep or horizontal or adverse. Okay, first we have to identify the slope. To identify the slope, there are some conditions that we have already discussed in the last class. Okay, suppose if your slope is mild, then your bed slope is less than critical slope and your yn value greater than yc value. Okay, this was the condition for mild slope. Now, from this diagram or by finding out the Froude number, we have already identified that in our case, our normal depth is greater than yc value. That means the slope here is mild. Okay, that means the slope here is mild because it gives us the condition of mild slope. Okay, because we all know in slope, mild slope, our normal depth is greater than yc. And for this equation, sorry, for this numerical, we have already identified that our flow is in subcritical, and whatever the flow is in subcritical, it always greater than yc value. So from here we can directly identify that our slope is mild. So first case is done. Okay, we got m. Okay, so once it is mild, then also we will be having some zone. Okay, so there will be m1 profile, m2 profile, and m3 profile. So our first case is to first find out the slope, then we need to find out in which zone this profile lies. Okay, so our very first case, we need to find out the slope, because whatever the profile, it depends on the slope. If it is a steep slope, then it will be S1, S2, S3. Okay, if it is mild slope, then it will be M1, M2, M3 profile. Okay, so first we have to find out it's a steep or mild or adverse or horizontal. Okay, so once you find out the slope, then we need to find out in which zone this graph lies or this profile lies. Okay, so we got this m value first. Now we need to identify it's m1 or m2 or m3. Okay, so what we do, for mild slope that we have already identified, we'll be having one. This is our bed of the channel. Then we'll be having CDL. This is CDL, and this is NDL and DL. Okay, okay. So now what it says, initially it was 1.5 meter. Okay, then it, because of the canal fall, it's reduced to 1.4, and which is greater than your yc value, that is your 0.43. Okay, so now this is your CDL and this is your NDL. Okay, for mild slope, your NDL, that is your normal depth, is greater than yc value. This is your yc, this is your yc, and this is your yn value. Okay, this is your yn value. Okay, this is your 1.4. Okay, or 1.5, whatever you want to consider. Okay, so initially it is 1.5. This is your above NDL is zone 1. The zone between NDL and CDL is zone 2, and then the last one is zone 3. Okay, so now your NDL is 1.5 initially, and because of the drop, your profile reduces to 1.4 meter. Okay, so in initial cases, in previous question, if you see, there is a construction of wire and your water level rises, so that is why from normal depth it got rises and it's in first zone. Here, due to the fall, there is a reduce in height of or depth of flow. Okay, and that is why it goes to second zone. Okay, so that is why our profile for this numerical is M2, as our profile lies in the zone 2, okay, in mild slope. So do you have any doubts? Okay, so we are going to end this class and again you join, okay? We will start with the next chapter, that is our hydraulic jump, or you can say rapidly varied flow. Okay?